For this, the final lecture today, I'm actually in my office rather than at my house. So I'm literally at the university, not just in the city. Yeah, no cat, unfortunately. My mother actually gave me a ceramic cat, so we have that. So she'll watch, don't worry. Okay, so we're going to do things a little bit differently today. We're going to talk about anyons first, and then we're going to talk about the fractional quantum Hall effect and what it actually has to do with anyons. And then we'll talk about experiments in my group and also in Cold Adams studying the fractional quantum Hall effect towards this goal of exploring anyons. So what are anyons? Before we can even answer that, I think we should start briefly by talking about the spin statistics theorem. Okay, so the idea is that we're going to have two identical particles, and I want to know what happens when I swap them past each other. Okay, so we're going to pretend we don't know that bosons and fermions are the answer, and just go back to the basics. So how does a swap actually work? Well, one way to think about it is that a swap is equivalent to taking your two particles, moving them both over, and then rotating one around the other. Okay? So we can say that the swap operation is equivalent to a translation times this rotation operator, which I'll call M. So we kind of know that the laws of physics are invariant under translation, so we can't really pick up any phases when we translate these particles in vacuum. So the question is, what can this M operator do where we bring one particle past the other? Okay, so the picture you should now have in your mind, let's draw these two particles. This is M, but this is also M, right? So the point is that if I have two particles here, this operator, which I can call B for braid, okay, brings one particle all the way around the other, okay? And so here's where things get kind of interesting. One can now imagine smoothly varying this trajectory, okay? And the idea is that moving a particle adiabatically through space doesn't really do anything. There's no discrete point where things should change. And as long as I live in 3D, so I can bring this loop up out of the page past the other particle, eventually I can just contract it down to a point. Okay? And so the point is that moving one particle around another particle in 3D is equivalent to the identity operator. It can't really do anything. So the point is that this braid operator, which, as we noted, is equivalent to the M squared operator, is the identity in 3D. Okay, and so what that means is that the M operator has got to be the square root of the identity, right? And the identity has two square roots, plus or minus identity, right? And so what that means, looking back up here, is that the swap operator is then plus or minus 1 in 3D, okay? And if the swap operator is plus 1, then we have bosons. And if the swap operator is -1, then we have fermions. Okay? And this is the spin statistics theorem. But here's the sort of interesting piece here. We relied very heavily on this fact that we could adiabatically deform this contour down to a point, right? And in 3D, this is no problem, right? Let's take this iPhone charging cable, right? And I need to get my fist out of this loop. Well, I can just move the loop around my fist and then contract it down to the identity. So that is to say, in 3D, there's no sense in which you can say even whether my fist is topologically inside of the loop or not, right? Because I can kind of continuously deform the loop around my fist. But the point is that in 2D, that's not the case. I can't take this loop out of the plane. And so as a consequence, something interesting may happen when the loop goes actually through that point. Okay? And so what this means is that in 2D, we so far cannot say anything about M. Or B, really. Okay? So this then raises an interesting question. Does that just mean that if I trap electrons or cold atoms or what have you in 2 dimensions, that their statistics might change, right? That this B operator might change? The answer is no, because the fact that I'm only moving my electrons in 2D doesn't mean that I can't perform this Gedanken experiment where I move them in the 3rd dimension, right? So if we want to study particles that have different B's or M's, we're not going to just have to study electrons in lower dimensions. We will have to study quasi-particles of 2D systems. Okay? By which I mean objects for which there literally is no 3rd dimension that you can even think about. These need to be excitations of those 2D systems. Okay? And so what we're hoping to find is that maybe this B operator will be e to the I phi, right? For phi not equal to 0 or pi. Maybe we can get some other phase, okay? And this would be a particle that you could never detect at a particle accelerator because particle accelerators are intrinsically 3D objects, okay? Another possibility is that B could be some unitary that depends upon the relative spins of my 2 particles, right? And then I'm implementing some kind of a quantum gate by bringing one of them around the other, okay? And this is what people call topological quantum computation. And the only point that I've made so far is that that can't exist in 2D, and we haven't proven that it, or in 3D rather, but we haven't proven that it cannot exist in 2D, okay? So what would it mean to have a phase here? Well, that would mean that when I bring one particle around the other particle in this direction, I pick up a phase e to the I phi, right? But unitarity means that if I bring the particle around in the other direction, I need to pick up a phase of e to the minus I phi, right? So what that suggests is something kind of interesting, right? What it says is, if we would like to have this physics, we're going to have to break time reversal symmetry. We're going to have to add some chirality to our system, okay? So the two ingredients that we know we need to have, we know we need to have a 2D system, and we know we need to break time reversal symmetry. And the third thing we know is that we can't just study electrons, right? We have to study excitations of some strongly interacting 2D system, right? So the natural thing to ask is, what happens if you take strongly interacting electrons in 2 dimensions in a magnetic field and look at the excitations of that system? Are they anyons? Okay? And the answer is going to be yes. And so the next thing we need to do is learn a little bit about the 2D electrons, or electrons confined to 2D rather, in a magnetic field and allowed to interact with each other. So on that note, we switch back to Keynote for a while. And we talk about the fractional quantum Hall effect. So before I go any further, because this story is kind of a whirlwind and I'm likely to forget, I would like to acknowledge the people who have done all of the experimental work that I've shown you earlier and that I'm going to show you today. Dave Schuster and his group are the collaborators on the circuit side, particularly Brendan Saxberg and Alex Ma, who's now at Purdue as faculty. And on the optical cavity QED side, Nathan Shine and Logan Clark are the real intellectual powerhouses behind the last set of experiments, and the machine is now in really capable hands with Claire Baum, Lucas Palm, and Matt Jaffe. Okay, so now we're going to have an experimentalist introduction to the fractional quantum Hall effect. Who has seen Landau levels before? Who has not seen Landau levels before? A couple of you. Okay, great. Well, hopefully you all get something out of this, but especially the people who haven't seen Landau levels before. So we put an electron in a magnetic field, and what we expect, ooh, is this animation not working? Well, that's sad. What's supposed to be happening here is when you put an electron in a magnetic field, you get, oh, it thinks it's working. Can you guys see the animation and I just can't? You can't either, huh? Well, that makes me sad. Because this is one of my standard slides, so I don't, okay, well, we'll figure it out. The point is just, if I put an electron in a magnetic field, I get cyclotron orbits. And it doesn't matter where in space I do this, I get these cyclotron orbits. And this might be a little surprising because if you look at the initial Hamiltonian, it doesn't look like it's really translationally invariant, right? Because this vector potential has an R in it. But it turns out that that's sort of a gauge dependence. It doesn't really matter what that means. But what you can take away is that it doesn't matter where you put your particle in the magnetic field, you get similar cyclotron orbits, classically speaking. Okay? If I increase the velocity of my particle, I get larger cyclotron orbits, but the frequency remains the same. Okay? And so we've learned actually then two important things. Important thing number one is that the system is translationally invariant. And the second thing we've learned is that the eigenstates appear at discrete energies in multiples of this cyclotron frequency. Okay? And so those two things together are really enough to tell us about what happens quantum mechanically. We know the eigenstates are spaced in energy by this cyclotron frequency because classically we just get these cyclotron orbits that are always at the same frequency, no matter the size of the orbit. And we also know, because there's a translational invariance, that there are going to be a whole bunch of eigenstates at each of these energies, okay, reflecting that translational invariance. And so these are called the Landau levels. And we're going to concern ourselves with electrons that are cold enough that they thermally only occupy this lowest Landau level, okay, and are then allowed to interact within that Landau level and organize themselves, okay? So the first question you ask is, what are the eigenstates of that Landau level? So you can specify these eigenstates in a whole bunch of different ways. A very nice way is to just specify them based on their angular momentum, okay? So the simplest eigenstate is just a Gaussian blob at the origin, and then I have rings with increasing amounts of angular momentum that are all at the same energy centered on that origin. And again, translational invariance says I should be able to do this centered on any point that I want, find a complete basis of eigenstates that look like these rings. And indeed, that's what you get if you're willing to perform a gauge transformation on this Hamiltonian. So let's write out what those eigenstates are. And the thing that's really powerful and nice that we're going to rely on is that we can work, instead of in two real coordinates, in one complex coordinate, which is x plus iy. So the real part of z is x and its imaginary part is y. So this is nice because now we can write these lowest Landau level eigenstates as z to the L e to the minus magnitude of z squared. So this piece is just a Gaussian factor that decays in space, and this z to the L moves the maximum out in radius to basically square root of L, okay? And gives us a phase winding as you go around the origin of 2 pi L, okay? And this is going to be very important for finding the eigenstates once we add interactions. So here's the thing that's interesting. We have these pairwise interactions between our particles, and classically you get all kinds of messy dynamics. Quantum mechanically, we just want to know the ground state of this Hamiltonian with all the particles living in the lowest Landau level. So the point is that we want to make sure our interactions are sort of contact interactions in space, okay? And that they're not so strong that they populate these higher Landau levels in the problem, okay? And if that's the case, we now have an interesting situation because all of the single particle eigenstates in the absence of interactions are at exactly the same energy, okay? But now, when we turn on interactions, we've got this huge family of states that absent the interactions are totally degenerate, and now the interactions, no matter how weak they are, essentially, can move the particles around between these eigenstates and hybridize them. They don't have anything to compete against, right? They are the only energy scale in the problem, right? And so the particles will order within this lowest Landau level. So the idea you should then have in mind is if I have a particle with 1 unit of angular momentum and a particle with 4 units of angular momentum, these contact interactions can basically make them collide and become a particle with 2 units and a particle with 3 units, or a particle with 0 and a particle with 5, and so forth. And so the point is that we need to find the ground state of this Hamiltonian in the presence of these contact interactions that not only give you an energy cost for having particles that overlap in their orbitals in space, as these orbitals do a little bit in their tails, but can also change which angular momentum state your pairs of particles are in. Okay, so what is the ground state of this Hamiltonian? Well, it turns out this was worth a Nobel Prize for Bob Laughlin. And for bosons, it will be a product over all of the particles, I and j, so all of the pairs of particles, of zi minus zj squared times this e to the minus sum over k of magnitude of zk squared. So why is this the ground state? Well, it's the ground state for one reason, for one thing, because you can see that if I is not equal to j, or is equal to j, sorry, if I is not equal to j and the particles are at the same location, the wave function is 0, right? So what this means is that this wave function keeps the particles from paying any contact interaction energy, right? So that's great. But the other important thing is that it has to live within this lowest Landau level, right? The particles have to live only within those ring orbitals that I wrote down. But we can see that this actually does that as well, because we can expand out this quadratic, or the product of these quadratic factors. And what you see is that the only thing you can get for any particular particle is that particle z to some integer power times e to the minus magnitude of that z squared, right? Which is one of those single particle orbitals. So it'll be sums of these monomials, right? But each monomial is made of single particle orbitals in the lowest Landau level. Okay, so far so good? So in the solid state, the signatures of this have to do with Hall conductivity and evidence of fractional charge and fractional statistics and so on and so forth. And so one question we're going to ask is, how do we make these states from light, and how do we understand them? But the first thing I would like to do is show you that the excitations on top of this ground state are anyons. So again, just to get an idea, how many of you have seen this derivation previously, the statistics of the excitations? Almost nobody. Okay. Are people following? Because this is pretty important for what's going to come next. Do people really follow why this is an eigenstate and why it's the ground state? Are we all comfortable with that, or should we stop and chat a little bit more about that and about these single particle eigenstates that I drew over here? We're comfortable? Okay. So, for delta function interactions, for contact interactions, it is an exact eigenstate. It's really quite amazing and magical. So if you want to look up more about what the approximations are, here, let me switch over to my iPad so I can give you some references and some terms to look up here. Can you see my iPad? Okay, great. So if you would like to look up what happens as you make your, as you move away from pure contact interactions, the term to look up is Haldane pseudopotentials. And the basic point is, the longer the range of the interaction, so if I call this my Laughlin wave function, Q here, we'll define this in this way. Product I is less than J, Zi minus Zj to the Q, e to the minus sum Zk squared. Okay? If I write this, the longer the range of my interactions, the larger this Q needs to be. Because the larger Q is, the higher the order of the zero in the interaction potential. Or excuse me, in the zero of the wave function, so the further apart the particles are kept. Does that make sense? So this is how that's typically parameterized. Okay, great. So, what is the next question? So I think the next thing we really need to do before we move forward anymore is build a little bit more understanding of this Laughlin wave function. So the question is, what is the density, the average density of this wave function? Okay, and so the basic point is, if I'm more careful, I should put an LB here, the magnetic length. Okay, and what we can see is that for any given particle, the highest power of Z, we can call this particle M, of Z to the M is, and then we're going to have N total particles, is Z to the Q times N. Okay, because the point is, if you fix I at 1, let's say, or M at 1, then J here can run over 1 to N, And then there will be one term where you get z to the mq, or nq, okay? And so the point is that we're going to have z to the nq, e to the minus zm squared over lb squared. And this has a maximum at a radius of root nq lb. Okay? And so what we know is that the effective area of the of this Laughlin state is root nq lb squared times pi, right? Which is pi lb squared times nq. Okay, so this is interesting because what this says is that, of course, the area scales linearly in the number of particles, as we expect. The area per particle is q times pi lb squared. Okay, and if you go back to the derivation, which I've skipped, of the fact that these are the eigenstates, what you discover is that one flux quantum has an area of pi lb squared. Okay, and so what this means is that each particle occupies, if you will, q flux quanta in space. That's kind of the area that it's covering. Okay, so so this is one important point. The other important point is that the density here is sort of 1 over pi lb squared times q. That's the density of our particles. Okay, great. And the other point is, this is just a definition now. The way people typically talk about this is a filling fraction of 1 over nu, which is defined as q. Okay, so if q is equal to 2 for bosons, right? And why does q have to be even for bosons? Because remember, it has to be symmetric under interchange of the particles, right? And this wave function will only be symmetric under interchange of the actual particles if q is even, right? So if q is 2, this would be called a nu equals 1/2 Laughlin state. You could have 4 here as well. For fermions, the lowest one is q equals 3. And this is what's called the nu equals 1/3 Laughlin state, which is the first one that was observed in experiment. Okay? So, the question is, what are the excitations on top of this ground state? Okay, so I'm going to come up here and I'm going to copy our ground state wave function down below so that we have it to look at and admire and appreciate because it's beautiful. The point is, I can define a wave function here, which I'll call psi of z whole, okay, is psi q times a product over all of my particles of Zi minus Z whole. Where Z whole, I haven't actually added any more actual electrons or photons or anything to my system, okay? All I've done is write a new wave function, which is the old one, but I've now enforced that the particles not only can't be on top of each other, but they also cannot be on top of Z whole. Okay? So we've effectively reduced our density a little bit, right? But the important point here is that the simplest excitations I can put in here doesn't have a Q in that exponential, right? It just has a 1 there. Okay? And so what that means is that sort of density-wise, I would have to put, Q of them in to have a hole in my thing corresponding to 1 full particle, right? The amount I have reduced the density by effectively is 1 over Q of a particle. Even though it really goes to 0 at that one spot, but like I haven't made a hole that when you integrate it up, subtracts out a whole particle. It subtracts out, or rather it moves the density outward such that there's a dip that accounts for 1 over Q of a particle. Okay, and so the interesting thing now is that this is clearly still an eigenstate of the Hamiltonian. Yes? Does that make sense? All we've done is we've added additional powers to our wave function, right? Additional powers of Z, which doesn't take us out of the lowest Landau level. It doesn't cost us any contact interaction energy. You could imagine that if you had a little harmonic trap on your system, just a teeny tiny one, this state is not favored compared to your initial ground state because you push the particles outwards in the trap a teeny tiny bit. So it's not the absolute ground state, right? But it doesn't cost any interaction energy to build. So this is an eigenstate. And now the question is, what is the charge of these holes that I've put into the system? So by charge, what I really mean is how much Aharonov-Bohm phase would I get from moving one of these things around? Well, how would you move it around? Well, to generate a density depletion, if these were cold atoms, you would shine in a laser beam, right, to repel the atom slightly. If they're electrons, you might push an STM tip in to repel the electrons a little bit. And then I want to know how much Aharonov-Bohm phase do I pick up when I move this STM tip or laser beam around in a circle. Okay? So I can define that as some Aharonov-Bohm phase gamma of a circle C is an integral around that circle, dZA, we're integrating this ZA around the circle, of psi of ZA, d by dZA, psi ZA, right? This is just the normal way that you adiabatically move a wave function and see how much phase you pick up, okay? So this looks horrible because, well, I've actually called it Z whole here. So let's just leave this as Z whole. It'll be a little cleaner. So this looks like a pretty messy thing because Z whole appears in this thing all over the place, right? And what we see is that, in fact, when we differentiate this thing with respect to Z whole, we will generate n terms, right? Each one containing this whole factor, but missing one of the n terms. Okay? And so it turns out the easiest way to get that is to kind of use a mathematical trick, which is to write this as follows: Z whole, d by dz whole, of a sum over all of my particles log of zi minus z whole times my whole wave function. And the derivative is now just of this piece here, because the point is, this derivative, when you take the derivative of that logarithm, it gives you 1 over each one of those z wholes, or each of those zi minus z wholes. Okay? And so this is kind of cute. And now what I can do is play one more trick here, which is to use a delta function and an integral over 2D space to remove the zi from this thing. Okay, so what I'm going to have now is I'm going to have an integral over all space of dz whole times log of z minus z whole. And then what I'll have here is z whole minus, or times, a sum over I delta zi minus z. Well, just an expectation value of that over my wave function. Okay, and the basic point is that this picks out zi equals z, and then puts that into this logarithm, or z equals zi and puts it into the logarithm. But the nice thing is, now we can identify this object as the density at z. Okay, and so in total, what we're now left with, which I think is quite beautiful, is dz whole, d squared z, d by dz whole, of log of z minus z whole times rho of z. Okay? And this rho of z we can just swap the order of integration here, and we get d squared z, rho of z, integral over my curve, dz whole, d by dz whole, log of z minus z whole. Okay, so why is this piece neat? Well, this is super cool, because what is the value of this integral? The point is that if I don't integrate z whole around z, right, I get 0. Right? This is like, it's like a topological thing. And so essentially what this does is it gives me the phase change of z whole as I integrate around this point z. So if z isn't inside, if z is over here, and I integrate like that, the total phase change is 0. If instead I integrate around z, my phase change is 2 pi, right? So what I'm going to get in total is minus 2 pi I here. Okay? And so in total, what this gives me is 2 pi times the integral d squared z of rho of z. Okay? Around some curve S that for which ds is equal to c. In other words, we were initially going around this curve C here, and S was going, and this integral was going over all space, right? But the only points that now matter in this outer integral now are the ones that are inside of that curve. And so in total, what I get here is essentially S over Q LB squared, right? Because remember, rho was 1 over pi LB squared Q. Okay, and so what this really says is, if this had been an electron, and we moved it around a closed contour, an electron acquires an Aharonov-Bohm phase of S over Q, or excuse me, of S over LB squared, right? Every time you go around one flux quantum, you acquire 2 pi of phase, right? And so the fact that we have an additional factor of Q here says that these holes that we've put in with our laser have a charge of E over Q. Okay? Okay, so here's where things get interesting. The basic point was all that we cared about was the integral of the density over the path of the charge. So how much did we say that an anion reduces the density? Or excuse me, one of these holes. It reduces it by 1 over Q, right? So what that means is if I made a wave function psi of z whole 1, z whole 2, right, which was my psi of Q times a product over I, z minus z whole 1, times a product over j, z minus z whole 2, right? Then the point is this cloud was going to have uniform density except for two regions here and there at z whole 1 and z whole 2 where the density is reduced a little bit. And what we showed is that if I just move one of these regions around, the amount of phase that the whole many-body wave function acquires depends upon how much density that hole went on top of, right? But now the point is, if that hole goes over the other hole, the effective integral is reduced by an amount given by 1 over Q of a charge, 1 over Q of a flux, right? And so what that says is that these anions have statistics. Can you still hear me? Have statistics 1 over Q. Okay? That is to say, if you braid one around the other, you acquire a phase of 2 pi over Q. Okay, and that is a topological phase, because if you braid one without going around the other, you get no phase. If you braid it around the other, you get this phase of 2 pi over Q. And it's discretized into those two values, right? Moving this charge, this anion around doesn't affect it, as long as you don't move them through each other. And when you move them through each other, you get these discrete jumps. Okay? Yes. So this is one of the many things that I've swept under the rug. A lot of rug sweeping goes into telling these stories in this simple way, and it's a piece of why definitively detecting these anions has been tricky. The basic issue is that I haven't told you how large the system is, right? Like what the boundaries are at the walls. Yes? So if there are no boundaries, then there are an infinite number of equivalent eigenstates that the system is equally happy to live in. right? You can make this Q that I've written here any even power that you want for bosons and any odd power that you want for fermions, and it just makes the cloud more and more dilute. Yes? And I can put in however many holes I want. So in practice, what you really want to do is have some, say, harmonic trap that makes the system prefer to have fewer holes. You want to pay a little bit of energy for the holes, but not too much. Okay? Exactly. But there's a subtlety associated with that as well, which is that microscopics usually dictate that you don't just have one Haldane pseudopotential, and the system would prefer to have a chiral Luttinger liquid at the edge, right? Which is to say, to make the system really, to build a gauge invariant Chern-Simons theory for this, you have to have a Laughlin state in the bulk and this chiral Luttinger liquid on the edge. And there's this chiral anomaly story that honestly, I'm an experimentalist, I don't fully understand, associated with that. If you can do this on a torus, the story is quite different, right? And this is something that we can do with photons. We can potentially put the system on a torus so that there is no edge to study at all, right? And if you can do that, then the system is all bulk, and you can put in the number of quasi-holes that you want. But to answer your question more concretely, Antoine, what's likely to happen is as you put in more and more holes, eventually it becomes favorable not to have more holes, but to organize instead of into a Laughlin state at nu equals 1/2, into a Laughlin state at nu equals 1/4, right? But that depends upon the specifics of the Haldane pseudopotentials, which one is preferred, and the specifics of the edge of your system and so forth. So the way people typically tell these stories, and it makes the papers admittedly rather opaque and confusing, is anything that depends on the microscopics, they pretend doesn't exist, right? And my suspicion is that that's the reason why it hasn't worked until recently in any experiments, because we're actually all very sensitive to these microscopics. So I do want to show you a little bit of data. But before I do that, I would like to refer you to two wonderful references on this topic. One is a book by D. Yashoika called, believe it or not, The Quantum Hall Effect. And the story that I just told you about anyons is on pages 97 and 100 to 101. And it really gives you a good flavor of what the rules of the game are and how to push ahead with these ideas. And the other paper that I like the most on this topic is a review article by Steve Girvin. And those are my two favorites. Okay, so in what time we have left, I would like to tell you about how to realize some of these ingredients and start to make Laughlin states out of optical photons. But before I do that, I would like to get a sense from Antoine of how much time he would like me to spend on this. What? 20 minutes? Okay, that was easy. That's plenty of time. Let's take a quick poll. Who wants me to spend 5 minutes? Nobody? Okay, you guys are that excited? It's Wednesday at whatever it is, 2 a.m. or whatever over there, and you want me to spend 20 minutes? Okay. Have you already eaten or you're about to eat? Oh, I see. Half an hour after. So I'm not making you late for dinner. Perfect. Okay. So let's talk about how to make Landau levels in optical cavities. Okay. So people use optical cavities for all kinds of science. Usually they think about single modes of cavities. What we think about is multiple modes of a single cavity. Okay. And there's now a community exploring that kind of physics, including Martin Weitz, and Ben Lev, Monica Schleiersmith, Tilman Esslinger, and others. They don't all use the same analogy that we use. So I'd like to just give you a quick flavor of what that analogy actually is and how we use it to study photons in Landau levels. So the picture is if you just take a two-mirror cavity, these are the two mirrors, okay? And you send light into it off of the central axis of this cavity. The photons oscillate back and forth in space. I claim, wow, that animation isn't working? Okay, this is a problem. I have to, yeah, these animations I can't do without. So just give me a minute. I'm gonna close Keynote and reopen it for you. I probably should have just done that earlier. Yeah, if we can't have animations at all, I may have to give you I'll have to act with my body, and that's going to be embarrassing for everyone. So I'm just quitting Chrome here to try to help my computer along on this journey. I'm actually just quitting everything and hoping, because it doesn't seem to want to reopen Keynote. There we go. Keynote is alive. Hurrah, there. Okay, let's see what we got here. And if the slides don't, and if the movies don't work, they don't work at this point. Okay, great. So here we are. Cross your fingers. Yeah, okay, great. The idea is you send this light into the cavity and the photons oscillate back and forth in space like a massive harmonically trapped particle. And the way you can understand that if you want is just by ray tracing the photons moving around in this cavity, okay? There's a Floquet picture you can think about looking in this paper from Ariel Sommer. But this is more or less enough here. The point is that the transverse momentum of the photon, that is to say the tilt of the ray, tells you about how fast it moves back and forth in the transverse plane. And the curvature of the mirror can change that tilt, right? And that change in the tilt changes the transverse momentum and effectively changes the speed. So as long as you coarse grain out the longitudinal motion of the photons, you can think of these photons as massive harmonically trapped particles. And it's actually really quite a nice analogy that works out beautifully. If you look at the modes of an optical resonator, they really are these Hermite-Gauss modes in space, and they're uniformly spaced in energy, just exactly like the eigenstates of a harmonic oscillator, quantum harmonic oscillator. So the point is, if you send a photon into this cavity off-center to either the right or the left of the axis, you can decompose that into the lowest mode of the cavity and the first mode. Those have different energies. So half a cycle later of that phase difference, this plus sign has become a minus sign and the photon is off the axis to the left side. So really it's exactly the same story as a harmonic oscillator, right? And the fact that we're coarse graining out the motion along the cavity axis means you should think of the photon as kind of oscillating back and forth and being delocalized everywhere longitudinally, but as long as we only look in this middle plane, it looks like a 2D massive harmonically trapped particle. Okay, great. Now, to make the photons collide, or excuse me, to add a magnetic field to this story, we need to twist the resonator. We need to take this story from 2 mirrors to 4 mirrors. And the idea basically is that if you just think about how periscopes work, if I look at a tree in a periscope, those two
brown objects are mirrors. The tree comes out right side up. But if I rotate one mirror with respect to the other, the tree comes out rotated by 90 degrees. And indeed, as I rotate the top mirror with respect to the bottom mirror, the image of the tree rotates. Okay? And so the whole idea of this cavity is to just take a periscope that's twisted at some fixed angle and add two more mirrors to close the path, such that on every round trip through the cavity, the ray trajectory gets twisted a little bit. Okay? So the basic point here then is that the lab frame now looks like a rotating frame, in that in addition to this harmonic trapping that we have for the photons, the path gets rotated around a little bit on every round trip due to this fixed twist of the cavity. And so we can understand that as a Coriolis force and a centrifugal force. And the Coriolis force is omega cross P, which is basically the same as V crossed with some B, and the B is set by the twist of the cavity. And the centrifugal force is a radially increasing outward force, which you just compensate with the mirror curvature, right? So that when you perfectly compensate them, you should get a Landau level for photons. And so this is some numerical data. Oh, that animation didn't play. I really don't understand what's going on here. The basic point is that these states should move down in energy and those states should move up, and these should turn into rings. So why they're not doing that is beyond me, but when we actually build the thing, basically we take super mirrors, we stuff them into a 3D printed structure, because otherwise these cavities are very difficult to get properly aligned. And you can look at the modes of the cavity as you kind of change the harmonic confinement. And when you get the harmonic confinement just right to cancel this Coriolis force, you get this family of degenerate modes. And we can now zoom in on those modes and see that by very carefully changing the harmonic confinement by the cavity length, we can make the modes degenerate to within a megahertz or two, okay? And so that kind of energetic degeneracy, if combined with interactions between the photons that are stronger than this megahertz energy scale, should lead to Laughlin physics, okay? So there are whole other stories that I'm not going to tell you right now about measuring the Chern number in this system and trapping these photons in a Landau level on a cone to measure other topological invariants. And we can talk about those after. If anyone would rather do that than eat dinner, if any of you are already cheesed out, we can talk about this stuff instead. But the important thing to talk about today, I think, is how do we make these photons interact with each other in a way that's compatible with these cavities. So have you already learned about Rydberg EIT? Yes. Okay. Fantastic. So the basic point is that we're going to do Rydberg EIT in our cavity. And so the point is that the cavity photons will be the photons that are slowed down by by a thin cloud of atoms that we put in the cavity, okay? And then we have some control field that we send in from the side. Actually, to get enough intensity, we send that control field through another buildup cavity because the beam has to be big compared to the modes of the cavity for things to work. And then the photons can collide in real space, and essentially what you find is that the speed with which one photon propagates through this gas of atoms depends upon its distance from the other photon. And so as a consequence, the second photon sees this kind of variation in speed depending on how close it is to that first photon that acts as a lens. And so this photon-photon lensing effectively gives us an interaction potential between our photons. And as Antoine pointed out, our interactions are not delta functions, right? So to get things right, one would have to consider the higher order Haldane potentials to really understand what goes on. But in practice, we just brute force it numerically. Okay, so what you should have in mind now, if we had a 2-mirror cavity, indeed we have a 4-mirror cavity, but if it were 2 mirrors, we have these massive particles oscillating back and forth in the cavity, and they drag with them a collective excitation of these atoms, right? They go back and forth through the atomic cloud. And so if we have 2 of them, the repulsion between the Rydberg atoms essentially acts as a repulsion between the photons, or one photon lenses the other, however you want to think about it. So the first experiment we do to test these ideas is load a magneto-optical trap of atoms into a conveyor belt, transport it into the cavity. When you look in the cavity, the mode goes this way. We've got this thick cloud of atoms that's about 100 microns by 100 microns. We then compress it down and cool it to half a microkelvin so that essentially the cloud is very thin in this longitudinal direction so that we have very strong interactions for photons that are at the same location longitudinally. And now we can do spectroscopy on this system. For experts, these are the vacuum Rabi peaks corresponding to P excitations of the atoms. This is the Rydberg EIT peak corresponding to a Rydberg excitation of the atoms. And so when we send photons through this middle cavity EIT peak, if there's only a single cavity mode, we should only be able to get one photon into the cavity. And if we try to send a second one in, it'll reflect off until the first one leaves, and then a second one can enter. And so the easiest way to see that that's going on is to look at the statistics of the photons leaving the cavity. And what we see is that when we detect one photon, for the next 10 or 20 microseconds, a second photon can never enter the cavity. And this is a very kind of wild thing, because this cavity is like 6 centimeters long, and yet it can only hold one photon at a time due to this tiny gas of atoms living in a single plane of the cavity. And so that was if you have a single mode of the cavity, you should think of this as like a quantum dot. But man, if we add this twisted cavity to the story, we should be able to study Laughlin physics. So what I want to do last here is kind of tell you how we study Laughlin physics, and I'll briefly show you the data. But I think the more interesting thing is, how do you build a Laughlin state in a system that in principle should support Laughlin states, right? I've shown you we have very strong interactions. In a single mode, we can only put one photon in at a time, right? And I've also shown you that we can make these states degenerate and make the states of a Landau level degenerate in the cavity. So the thing really should just give us Laughlin states, right? But the point is, having a system whose ground state is a Laughlin state is not the same thing as having a Laughlin state, right? You have to have some way of preparing it in that state or cooling it into that state or something. And so I'm going to give you a bit of a protocol to do that I think gives you some pretty cool intuition about what this Laughlin state actually is. So we have this cavity, which for now we're going to say it has 3 modes: L equals 0, L equals 1, and L equals 2. And remember, these modes are defined as shown on the right here. What happens if I shine light into the L equals 0 mode of this cavity? Well, that's what we were just doing in the last couple of slides, right? I showed you the cavity gets blockaded. We can put in one photon, but we can't put a second one in, right? And once there's one in there, all future photons reflect off until the first photon leaks out. But what happens if we excite the cavity on L equals 1? Well, the point is, okay, this is a ring mode. It's a little bigger. Maybe you would say there should still just be a blockade, right? We can't put 2 photons into the cavity at the same time. But remember, if we managed to put 2 in, not only is there an energy shift, but they can also collide and exchange angular momentum, such that we end up with 1 photon with 0 units of angular momentum and 1 photon with 2 units of angular momentum. I hope this is sounding familiar from what we talked about earlier. So the question then is going to be, is there some 2-particle eigenstate, which is a combination of 2 photons, each with 1 unit of angular momentum, and 2 photons, one of which has 0 units and one of which has 2 units? Is there some combination of those 2 states that has 0 interaction energy, right? Because if there is, then when we try to excite the system, we will excite it into that superposition state, and that's the state that will leak out the other side of the cavity. And in fact, we know that there is such a state. It's Z1 minus Z2 squared times this exponential factor. And the way we can see that is we just expand out this quadratic, right? This is Z1 squared Z2 to the 0 plus Z1 to the 0 Z2 squared minus 2Z1 Z2, right? So 2Z1 Z2, that's we put in 2Z equals 1 photons, but they can collide and become Z1 squared, which is the first photon has 2 units of angular momentum, Z2 to the 0, the second photon has 0 units of angular momentum, right? And so the point is, this state has no interaction energy because, as we showed a long time ago in this talk, the photons avoid each other, right? But if we had a plus sign here, they would not avoid each other. they would be close to each other and we'd pay a large interaction energy. You can think of that as like an anti-Laughlin kind of state. And so the point is, if we shine light into this cavity, what we expect to come out the other side, even though we put in 2 photons with L equals 1, what we expect to come out is a 2-photon Laughlin state. And so you should think of this as kind of like a strongly interacting photon collider, topological photon collider Laughlin filter object. Okay? And so we actually have built this. It says Nature and Press. It's now published in Nature, but if you want to see it for free, it's this archive paper. And so the game is to send in light with angular momentum using a DMD, let it scatter through the cavity, and then measure the relative angular momenta and relative positions of the photons coming out with single photon counters and optical mode sorters. Okay? And so in practice, if we do this kind of experiment and we look at all the photons coming out in a single mode limit, what we see is that, man, we can only send 1 photon through this cavity at a time. But if we do this in a multi-mode limit in this Landau level, there's some suppression of pairs of photons kind of coming from the finite range of the interaction, but it's not a perfect suppression, meaning that pairs of photons do go through at the same time. We're building some kind of a correlated state. And so sufficient to say we can look at the individual modes of the cavity, these 3 modes that we were talking about. We can measure the correlations between photons coming out with the lower angular momentum and the higher angular momentum, and they come out in pairs. We can also see in space that these photons are avoiding each other, which tells us that we don't have a statistical mixture of these states. We actually have a coherent superposition, and sort of all taken together, this means that we've built this, this Laughlin state of light. And so there are all kinds of, I think, really cool ideas that one can think about going forward for braiding anyons in these photonic systems, and we can talk about that if anybody's interested. I think there's some neat protocols there coming from people like Fabian Grutz, Michael Fleischauer, and Misha Lukin, among others. But I think it's a very exciting time for topological physics in general, cold atom realizations, photonic realizations, solid state realizations, what have you. I'd like to refer you actually to one other paper that I forgot to write down, but that I think doesn't get the press that it needs. It's a paper by Nate Gemelke and Steve Chu. It's the first demonstration of fractional quantum Hall physics in cold atoms. Okay? It's a 2009 paper, and it's only available on the archive. And it is amazing, and everyone should read it. I think it's 2009, maybe it's 2008. Basically, what they do is they make single lattice sites, and they rotate the lattice sites by making them a little bit elliptical. And they've managed to see much of this same kind of physics. And it's somewhat controversial. It was never published in a journal. My sense is it's a wonderful paper. Whether it's exactly right or not is less important to me than that the ideas in the approach are extremely instructive for how this kind of science can work moving forward. So with that, I hope you've learned something. Even if all you've learned is that you don't enjoy talks from John, that's fine. You learned a thing. So I've enjoyed telling you these stories, and I do hope you've at least somewhat enjoyed listening to them. So. And if you don't want to clap, now is the time. So this is a really interesting thing, actually. The fundamental point is, why do we care so much about the sign of the interaction in general? I would say it's because in some ways our systems tend to be connected to reservoirs. Okay? If you have a system that's connected to, like a dilution refrigerator, and the particles have attractive interactions, well, as they move together, they can shed their extra energy into the dilution refrigerator until they collide, right? But if they couldn't do that, there would be some symmetry between attractive and repulsive interactions if the potential shapes were the same, such that we wouldn't care. So then you say, but I thought cold atom experiments were unitary. Why do we care whether the interactions are attractive or repulsive there? Well, I can tell you two things there. One is there are beautiful experiments from Uli Schneider and Emmanuel Bloch preparing superfluids at the edge of the lowest Brillouin zone for cold atoms in the presence of attractive interactions, right? If you can change the sign of the interaction and you can change the sign of the mass, it's as though nothing changed. But in practice, the problem is in the presence of attractive interactions with cold atoms, you get two-body loss when the particles get close together. And so what that means is that, in fact, you're still coupled to a reservoir with cold atoms. So as a consequence, this symmetry between attractive and repulsive interactions is still broken. Now, the reservoir is one that you didn't want, right? It's this reservoir in the continuum of like molecules flying out of your trap generated through these attractive interactions. But it's a reservoir nonetheless. If you really have a system that isn't coupled to a reservoir, or isn't coupled to a reservoir that can tell the difference between the sign of the energy, then you really don't care whether they're attractive or repulsive, I would say. And so we have some experiments with microwave photons where we have attractive interactions and manage to dissipatively stabilize a Mott insulator, right? Because in some sense, the point is, if you add a reservoir that dissipates out low energy excitations instead of high energy excitations, then you effectively cool your system into an excited state rather than into a ground state. Does that kind of make sense? So I think a related comment to make is that with Rydberg polaritons in free space, the default thing that you get is these attractive interactions. And if you try to change the sign of the interactions by changing the sign of your EIT detuning, you also change the sign of the mass of the polaritons. And so basically it's a wash, right? That has been solved in some sense by Vladan and Misha by adding an additional control field. But I think fundamentally the situation is different for cavity polaritons because we have additional degrees of freedom in the cavity geometry to change the sign of the mass directly by just adjusting the cavity length slightly. So as a consequence, we can actually get either attractive or repulsive interactions by default in these cavity setups. And this is not kind of unique to us. If you study cavity polaritons in the COOP rates, you can do this. If people want to look at a really exciting speculative system for studying strongly interacting and potentially eventually topological physics, look at COOP rate polaritons. And you know, that's a platform that's really up and coming. You don't need any cold atoms. It's just a solid state sample that hosts Rydberg excitons. It's really wild. Okay. Yeah, I'm sorry. I'm sorry. You know, I realized that I didn't get the timing quite right on these lectures. This was the material I really wanted to cover today, but I felt like I had to do some circuit stuff too. So this one was a little much. But this will be great. You'll all sleep well tonight. Thank you, guys. Take care. Care if I-